Alright, let's take a look at our sequences final. So, making sure you guys are ready for this. And let's get going on it. May have a different title on your paper, but that's alright because we're still dealing with sequences. Okay, you'll still see the same pattern. So, on these first ones, we're just telling us, is it arithmetic, geometric, or neither? So how is it growing? Remember, arithmetic, adding or subtracting, geometric, multiplying or dividing by the same number, both of them, neither, some other weirdness going on. Okay, so 0.5 to -2. Well, we could, always think arithmetically first. So I could subtract a 2.5. But if I keep subtracting 2.5, will we get to +8? No. So it's not arithmetic. So let's try geometric. 0.5 to get it to -2. Well, we could times that by 4, right? Well, -4, I guess, right? To get it to -2. If I take -2 and times it by -4, is that giving me a +8? It is. So this one's geometric. Okay. Second one, -1 to -2, -2 to -6, -6 to -24. I should tell that I can't subtract 1 each time to get it work. What about timesing by 2? If I times by 2, that'll get to -2, but timesing by 2 won't get to -6. You'd have to times by 3. So, this is a neither. Okay? Even though we're multiplying in our pattern, we're not doing the same number. Now, number 3, we've got 2 to -4, -4 to 8. When you're doing that opposite pattern, you should know that it's going to be multiplication. So if I times by 2, that'll work my numbers, right? And just make it a -2, so geometric again. Okay, number 4, -3 to -1. Well, we could add 2 to get there. -1 to 2, we'd have to add 3. 2 to 6, we'd have to add 4. So that one's going to be a neither. On number 5, 39 to 49 to 59 to 69. Should be pretty apparent that we're adding 10 each time. Arithmetic. And the last one, -6 to 194, 194 to 394, 394 to 5. It's easier to tell that we're adding 200 on the rest of these, but is -6 plus 200 194? Yes, it is. So, arithmetic. Alright, now, remember, when it asks for a common difference, all it wants to know is what number are you adding or subtracting by. So a common difference means that it has to be arithmetic. But we want to know what we're doing it by. So, how do I get this to add? Well, we're not adding, we're subtracting 10. Suppose you could put adding -10, same thing. That's our common difference, minus -10. They usually do D equals -10. For 8, we go from 14 to -16, -16 to -46, -46 to -76. So we're subtracting 30 each time. So D equals -30. Now for the common ratio. Ratio means it's a geometric, right? Difference, arithmetic. Ratio, geometric. What are we multiplying by? 2 to 8, we times by 4. 8 to 32, we times by 4. Same pattern. If you didn't know the pattern, take this number, divide it by that number. That should give you the pattern. So, ratio is often R, so R is equal to +4. Okay, -2 to 12, 12 to -72, 432 to -72. If you weren't sure, you could go 432 divided by -72, and you get -6. Does that follow the pattern? It does. So R equals -6. That's our common ratio. Okay, now finding the next 3 terms, we just figure out the pattern, and then we do it for 3 more terms, right? So 20 to 12, 12 to 4. Always start thinking arithmetically. So 20 to 12, we subtract 8. If I subtract 8, does that get me to 4? It does. If I subtract 8, -4? Yep. So subtract 8 again. We get to -12, subtract 8, -20, subtract 8, -28, and there we go. There's our first, our second, and our third answer. For 12, start with arithmetic. -2 to -12, we subtract 10, right? If I subtract 10 again, will we get to -72? Doesn't work, so it's probably not arithmetic. So let's try multiplication. I could times by 6, and that would get me to 12 times by 6 again. Yep. So we're timesing by 6. So you may need to get your calculator out as we get the next 3 terms. So we're timesing by 6 each time. So we times by 6, 432, negative 432. We get negative 2592. Times that by 6. And we get negative 15552, 15,502. And times that by 6. And we get negative 93,312. Okay, because we're times by 6 each time. I might have said times by negative 6 there, but I meant times by 6. We didn't change those. Alright, so there's the first 12 problems. Okay, fairly straightforward, dealing with the more basic aspects of dealing with sequences. Now we're going to get tougher. Recursive formula. Okay, remember, recursive formula has 2 parts. Where we're starting, okay, often called the f of 0 or f of 1 term. Either one works, depending on if you're calling this the 0 term or the first term. Okay, equals whatever number that is. Then you've got the pattern. How do we talk about the pattern? Well, we say the previous number, and then whatever the pattern is, if we're adding 2 or multiplying by 3, is equal to the next term. Okay, so next term equals previous in the pattern. We write that as f of n for next equals the previous f of n minus 1 and then the plus 2, or the times 3. Okay, so that's what we're dealing with here. So let's take a look at this one. So we start with negative 21. So I write f of 0 equals negative 21. If you wrote f of 1 equals negative 21, that works as well. Either one works. It depends on how you think of that first number. So both of those would work. Then we go f of n equals f of n minus 1. And what are we doing? What's our pattern? Negative 21 to negative 13, we could subtract 8. Negative 13 minus 8, is that negative 5? Minus 8 is positive 3, yep. So we minus 8. That whole thing is our recursive formula. Okay? Now let's try 14. So, once again, f of 0 or f of 1, same thing, equals negative 4. Then f of n equals f of n minus 1. And what are we doing to it? Well, negative 4 to 12, 12 to negative 36. Negative 36 to positive 108. So we probably multiply. So we could multiply by a negative 3 to get that to work. Does it follow through with everything? Check it. Yep. Check those answers. So we're timesing by a negative 3. And there's our other recursive. Okay. Now, this is for the arithmetic means and geometric means. Okay. So remember, for the process is you take the last number, and because this is arithmetic, we know we're adding each time. So I do the opposite. I take negative 987 and I subtract 13 from it to get me negative 1000. Okay. Now we've got to figure out how many jumps we've got. So or how many times we're adding. 1, 2, 3, 4. So we've got to take that and we've got to divide it by 4. We've got to split it into those pieces, 4 equal pieces. Repeated addition, the shortcut, 4 plus 4 plus 4 plus 4 would be 4 times 4, because there's 4 groups of 4. So to undo that, we do the opposite of multiplication, which is division. So negative 1000 divided by 4 should give us negative 250. Just double checking it to make sure I'm not leading you guys astray. So we are subtracting 250 each time. Okay, so then to complete that, probably need some extra space. To complete that, that tells us where we're going by. So 13 minus 250 is negative 237 minus 250 is negative 487 minus 250, negative 737 minus 250. Oh, we did something wrong, didn't we? And I was leading you guys astray. So much for checking my answer. There's 4 zeros, but how many times do we have to add? 1, 2, 3, 4, 5. Okay, remember, add 1 to that or you'll make the mistake that I did where we get to our answer too quick. Okay, so there was actually 5, so we should have divided by 5 because it's how many jumps we're making to get to our next numbers. So that would be negative 200. Okay, so 13 minus 200 is negative 187. So that term's negative 187 minus 200, negative 387 minus 200, negative 587 minus 200, negative 787, and minus 200, negative 987. So you've got to make sure you get that right division sign. So that was actually a pretty good mistake, because that would be a common mistake for people to make, because you just get going and then you forget to do that. Okay, so those are the 4 terms that we're dealing with, our A, B, C, and D terms, if we were to talk about it that way. Okay, so let's take a look at 18. So now it's geometric. So geometric, we're timesing, right? So we're going to times by the same number 3 times. Because we're timesing, we think opposite. So we take 108, 108, divide it by the first number, so last divided by the first. Okay, 108 divided by 4 gives us 27. Then we've got 3 pieces, so we've got to split 27 up into 3 numbers that are being multiplied by each other. Okay, so the shortcut way of writing repeated multiplication is through powers. So it's like question mark cubed. So how do we undo that? Well, the way we undo powers is with roots. The way we undo a square is with a square root. The way we undo a cube is with a cube root. If it was a fourth, we would do it with a fourth root. If it was a 5, a fifth root, and so on. So we got to take 27 and find the cube root of that. Basically, what number times what number times what number gives us our answer. Now, your calculator, you can just type that in, and the calculators have that functionality. Talk to your teacher if you need to figure out how to do that. And we get 3. So we're times them by 3 each time. So 4 times 3 is 12, times 3, 36, times 3 is 108. Now, if you didn't have a calculator, you could figure this out doing a prime factorization. 27 is like 3 times 9, 9 is like 3 times 3, 3 times 3 times 3, there's our 3 numbers, so our answer is 3. Okay? Alright, now these last ones are dealing with finding the recursive and the explicit equation, and then just kind of tying it to a graph. So the first 2 are just tables, so graphing it is pretty simple, right? So I've got 0 and negative 1, so there's negative 1, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4. So we'll graph in green. So 0, negative 1 would be right about there. 1, 1 would be right here. 2, 3 right here. And 3, 5. Oops. 2 3s right here. And 3 5s right here. So there's my graph. Okay? So that's the easy part. Now, recursive and explicit. Recursive, remember, we start with our starting point. So I go f of 0, saying when my input is 0, what is my answer? It's negative 1. Then, what's our pattern? Negative 1 to 1, we're adding 2 each time, right? So I go f of n equals f of n minus 1 plus 2. Okay? Then for the explicit, okay, it's kind of the same thing. We go f of n, or you could even put y, we would accept that, equals, where do we start? Now just think about your output. We start at negative 1. So I write negative 1. What am I doing to it? Oh, I'm adding 2. How many times am I going to add 2? Well, we don't know, but repeated addition is multiplication, so we times by our variable. Now some of you may want to rewrite it as y equals 2n minus 1, same thing. but that's the basic idea with our explicit. Okay, look at 18. Works the same way. So, 1, 2, oh, we go clear up to 81, don't we? So I may have to label this one a little better. So let's start with 81. Let's figure out what our pattern is first. 3 to 9, we can times by 3. 9 times 3 is 27 times 3. So we're tripling, we're timesing by 3. So the recursive, that's easy to deal with. So f of 1 equals 3, comma, f of n equals f of n minus 1 times 3. Now, to do the explicit, we've got to jump back to our 0 term. Okay? So, what number would jump back and then multiplied by 3 would get us to 3? In other words, do the opposite. What's 3 divided by 3? Oh, it's 1. So we start out with 1. So we'd go f of n equals our starting number, 1. And then what are we doing to it? We're timesing it by 3. How many times? Well, multiple times. And then we think repeated multiplication is actually a power, an exponent. So I take my variable and make it an exponent. So it's f of n equals 1 times 3 to the n. Now, you could have rewritten this one as f of 0 equals 1 if you'd gone back and done it that way. But for the recursive, it really doesn't matter which one you use as long as you get one. It's just easier to think about the first one. So I'm taking these down by a third. So 81 cutting about a third. Would probably be about here. So 27. Cut that in a third. About here. 9. Cut that in a third. 3. And then 1 would be really close to the bottom. So 1, 2, 3, 4. So 0, 1. 1, 3. 2, 9. 3, 27. And 4, 81. And we get that curve, which is typical of our geometric. Okay? There we go. Now, number 19 says, Mycroft is looking at his stamp collection. He has 4 stamps currently. He will become the best stamp collector in the world. To do this, he decides to double his stamp collection every week. So the way you have to think about this, and the easiest way to deal with this, is to make a table. Alright, so we got to think about where did we start. Okay, so we've got, we haven't started collecting any, and he's got 4. Okay, so every week he's going to double that. Well, what does it mean in math to double? We go from 4 to 8, 8 to 16, so we're essentially timesing by 2 each time, right? And, keep going until you get to a variable. Okay, so that's what he's doing. So, fairly easy to graph, right? And you don't have to graph all of them. We can just go, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. We'll go to 32. And then we've got 1, 2, 3. So then let's graph it. 0, 4, about right there. 1, 8, about right there. 2, 16, about right there. And 3, 32. And that's enough to kind of get what's going on with this curve. So, you can tell that this is a geometric situation going on. Okay? Now our recursive. So where do we start? Well, we start at f of 0. What does it equal? Well, it equals 4. Okay, think of your, I probably shouldn't do that at the same time. Okay, well, no, I will. Think of our explicit. Okay, we'll call this x and f of x. So f of x equals, where did we start? We started at 4. Okay, then what are we doing to that 4? Well, to get the next term, we're taking the previous term and timesing by 2. So for this one, we take that 4, what do we do to it? We times it by 2. Now as we keep going down till we get to our variable, how many times have we times by 2? X amount of times. Okay? Just like if I stopped at 3, how many times would I have times by 2? 1, 2, 3. Well, what's 2 times 2 times 2? It's 2 cubed. That is the same as a variable. So if this is x, the x is a variable. Remember, with geometric, whenever you're timesing, your variable is an exponent. If it's not, it's wrong. Okay? It's a very critical part to that. Alright? So, one last problem. Okay, now we've got some furry little dudes here, so we're using this pattern. Okay? And once again, I would always suggest making a table. I think the table is the easiest thing to see this with. So, in the beginning, that's like 0, right? There's 2 of them. So, in the beginning, we have 2. Okay? We'll use x and f of x. Yeah. Okay, now, after the first hour, we now have 6. Second hour, we now have 10. Third hour, we now have 14. So what's the pattern? Well, we're adding 4 each time, which would make this arithmetic. So graphing it would be pretty easy, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, we'll go one more just for fun. 1, 2, 3, 4. Then we graph those. So 0, 2, right about there. 1, 6, right about there. 2, 10, right about there. 3, 14, there, and 5, 18, or 4, 18. And there we go. That shouldn't have had a curve in it. But my graph, that guy apparently needs to be bigger. There we go. Now the recursive and the explicit. So the recursive, we start at f of 0, because that's our input. What does that equal? It equals 2. Now, what's our pattern? Well, to find the next number, we take the previous number and we add 4 to it. There's our recursive. Now for the explicit. Start with your f of x equals, okay, so I think we have like x coming down here. So now, where did we start? We started at 2. What did we do to 2? Well, we added 4 to it. How many times? We don't know. A variable number of times. But think about it again. Let's say we went down to the third. How many times did we add 4? We added 4 3 times. What's 4 plus 4 plus 4? Well, it's obvious that it's 12, but how do we write that quickly in a shortcut? It's 3 times 4, or 4 times 3, same thing. Okay, 3 groups of 4. So if I have an x amount of groups, I'm timesing 4 by x. If when you add, when you have an arithmetic sequence, you're not timesing by the x, you're doing it wrong. Some of you may want to change that to be y equals 4x plus 2, so it looks slope-intercepty. That's fine too. Okay, but that's all we got, guys. So as soon as you get that done, you'll be feeling good, got your test, you'll be able to sit in your chair, finish the test, and you'll be like, woohoo! I am the greatest! And you'll get your test back. Actually, we'll probably be doing it on the calculators, so you'll get your test score back, and you'll be like 100%, and you'll be like, woo! Your mouth open wide, your teeth, and you've got a little something stuck in the back of that one. Should have brushed better. So you've got your hair. Oops, probably should put some clothes on you, because you shouldn't come to school naked. Okay, I'm not sure what kind of clothes those are, but they work. And then you'll go home, and on winter break, you'll just be able to sit on your bed and do nothing. And let's put your covers over you. And apparently you're sleeping on your head.